So let's talk about sound intensity. There are two things that we want to look at. What is sound intensity and how is it measured? And we want to determine how to express sound intensity in units called decibels. Now, when we talk about sound intensity, we're talking about the loudness of the sound. And recall that whenever we have a wave transports energy. When a wave moves through the medium itself is not transported. Energy is transported through the medium. In the case of sound, we know that the air particles are compressed and rarefacted, but the air particles themselves don't move through air. It's the energy that travels through the air. The air particles just move back and forth in simple harmonic motion. So intensity of a wave, when we refer to the intensity of the wave, we're talking about the energy transported per unit time per area. Now, energy transported per unit time, that's called power. So intensity is equal to power divided by area. So the units for intensity are watts, units of power, divided by meters squared, which are the units of area. Now we know that power can be expressed as work divided by time or energy divided by time. So the units could also be energy per unit time per unit area, or joules per second per meter squared. Now if we talk about sound being produced, sound travels in all directions from the source. So here I've depicted our source of sound as that green dot. Perhaps it's someone just yelling out or singing out a note, or a speaker putting out a sound, and the sound's traveling in all directions. Now the fact that it's traveling in all directions in 3 dimensions, we know that the energy is going to have to be shared over that large area. And the further the sound travels, the more we have to spread that energy around. So the sound intensity will decrease as you move away from the source. So what I have here is I've depicted sound waves circling the source. Now keep in mind this is in 3 dimensions. So the intensity decreases with distance between the source and the observer. The observer would be indicated where these red lines are. So intensity follows what's called an inverse square law. And the inverse square law compares 2 variables where it's an inverse relationship. But not only is it inverse, but it's an inverse square relationship. There are many things in our universe that behave following the general idea of an inverse square law. So intensity is proportional to 1 over r squared. That's a proportionality sign. It kind of looks like an infinity sign trimmed on the end. So with this in mind, if r doubles, the intensity decreases by 1 over r squared, or 1 over 2 squared, 2 because it's doubling. So that means that the intensity will actually go down 1/4. If it was just an inverse proportion, if we doubled the radius, then the intensity would be half. But since it's following an inverse square law, it's 1/2 squared. So if we triple r, I decreases by 1 over 3 squared, or 1/9. So if we triple the distance compared to our original, what will happen is the intensity will go down 9 times. It'll be 1/9. And the reason it's 1/9 is, again, it's following the inverse square law. If it was just an indirect proportion, if I was proportional 1 over r, if it was that, then it would be 1 over 3, so it would be 1/3 as intense. But that's not what the law is. It's an inverse square law, so it would be 1 over 3 squared, or 1 over 9. Now, if we take our original formula, I is equal to power divided by area, and we substitute the formula for area, we end up getting intensity is equal to power divided by 4 pi r squared. And that's where the r squared comes from. Now, a few facts about sound intensity. The smallest sound, a sample would be 1,000 hertz, which is about the midpoint of hearing for a human being. Now, I said earlier that humans can hear between 20 and 20,000 hertz, but we don't hear the same intensity of all of those frequencies. So the midpoint of hearing is about 1,000 hertz. So given that that's the midpoint, a human can hear about 10 to the minus 12 watts per square meter. That's the smallest sound that we can pick up with our ears, on average. So we call that the threshold of hearing. Now, because that's an average, that's our standard that we've selected, 10 to the minus 12. Now, in contrast, if we hear a sound which is 1 watt per meter squared, we call that the threshold of pain. That's when our ears start to hurt. And if you continue listening to a sound which is 1 watt per meter squared, prolonged listening to that will cause permanent ear damage or hearing damage. You'll lose your hearing. So if you think about it, a range from 10 to the minus 12 all the way to 1, that's a huge range. And because it's so large, our perception, how our brain interprets what our ears, the signals our ears are sending to our brain, we don't depict sound as a direct proportion. So if I double the loudness, I don't, or double the intensity, I don't hear it as twice as loud. It's different. To perceive a sound that is twice as loud, the intensity has to be 10 times as intense. Twice as loud requires 10 times the intensity. So for this reason, we measure sound using what's called a logarithmic scale, or basic logs, log, using units called bells, proposed by Alexander Graham Bell. And we actually package these in decibels, so 1/10 of a bell. And by definition, 10 decibels is equal to 1 bell. Now, intensity level, symbolized by Greek letter beta, capital beta, in decibels, that's the standard. Intensity level is equal to 10 times the log of the ratio between the intensity of the sound measured in watts per meter squared, divided by our standard, which is the threshold of hearing, the smallest sound that you can hear. And that's 10 to the minus 12 watts per meter squared. Now, just some common examples of things. You don't have to memorize any of these, but I just want to go over the list to give you an idea of where these sounds stand on the logarithmic scale, as well as the scale using watts per meter squared. So a jet plane is very loud at 30 meters away, has a sound intensity in decibels of 140. That would be very painful, and that's the reason why people that work on the tarmac next to where the planes are moving around in the airport, that's why they have to wear hearing protection continuously. 140 decibel calculates to 100 watts per meter squared. Now, these conversions you can do using this formula. To use the formula, you have to be familiar with log operations. And if you're not, you're going to have to talk to me about that in class. Threshold of pain we've identified as 1 watt per meter squared. That's equivalent to 120 decibels. Rock concert, which you may attend, realize at that concert you are listening at a intensity of the threshold of pain. Now, depending where you are at that rock concert, if you're next to the speakers, you're going to be getting hearing damage. Imagine the people that work those concerts continuously. If next time you're at a concert, see what they have stuck in their ears. They all wear hearing protection. And that's our threshold of pain of 1 watt per meter squared. A siren, ambulance siren, or police siren at 30 meters away would be 100 decibels. Inside a car traveling at 55 miles an hour, of course depending on the car, but on average, you're talking about 75 decibels. A conversation, a normal conversation at a distance of a half a meter away from whoever you're speaking with, that would be 65 decibels. A whisper would be 20 decibels. Rustling of leaves, 10 decibels. And threshold of hearing is 0, and the reason it's 0 is because this ratio here ends up being 1, and log of 1 is going to end up being 0.